we have to start really from the molecular design level to understand what it takes to make this type of new electronic materials.
Electronic skin, or e-skin, is set to change the future of medicine, consumer electronics, and even more. Zhenan Bao has spent decades working on this technology, discovering ways to create electronics that are conductive, stretchable, biodegradable, and even self-healing. Dr. Bao is MRS's 2025 Fred Kavli Lecturer and is here with us now to discuss this incredible work. Such a pleasure to have you with us today.
Nice to meet you.
Well, thank you for your time. All right, I want to get started with something that's a little bit of a different question, because you previously mentioned that Wolverine from X-Men inspired some self-healing electronics. Can you tell us a little bit more about how that played out?
Sure. Well, our skin is not only flexible, but also stretchy and can self-heal when there's wound, and also biodegradable. So self-healing is something that we wanted to be able to incorporate in our skin-inspired electronics. So therefore, we have to think about it in a way that we can use artificial materials to mimic this capability that's often seen in science fictions. So we were able to achieve that by designing a specific type of polymers that have bonds that can reversibly break and recover, therefore to heal the material.
Interesting. It's a little bit of life imitating art there, just a little bit. All right, what do we have to gain from crafting electronics to behave more like skin?
So with all the functionalities human skin has, the skin is what allows a human to be able to interact with surroundings, and also it's a large organ that covers, protect us from external infection, bacteria, and virus. So if we can make the future electronics and especially sensing systems to have the similar form factor as human skin, then our electronics don't need to be rigid and brittle anymore. Then they can get closer to the surface of the human body, or even go inside human body, so that we can measure information that's related to human health, such as electrical signal, chemical signal, biochemical signals more accurately, and to allow us to understand our health, and also to identify disease before they start to show symptoms.
I can't imagine this was easy to develop electronic skin. What were some of the greatest challenges that you ran into, and how did you come up with some solutions for those problems?
Yeah, the greatest challenge we had is the electronic materials that are skin-like, that is as soft as jelly, but at the same time have great electronic properties. They did not exist before. So we have to start really from the molecular design level to understand what it takes to make this type of new electronic materials. And then even after we come up with the material, it took us 10 years to really get those materials to be good enough electronic materials to be used to actually make sensors, make integrated circuits. But then taking the materials to incorporate into the system also requires further understanding of how to manufacture them and how to control their properties from the molecular to nano to macroscopic scale to eventually to make these wearables and implantables.
Incredible. Now, I know that you've collaborated with a number of different groups, but you've worked with surgeons at Stanford. How did that help you determine how to monitor a patient's recovery?
It was really eye-opening to watch a surgery for deep brain stimulators to be implanted into Parkinson's disease patient. That really allowed me to see what it takes to get a device into human, and in turn think about how we should design our materials to meet all the requirements.
With regard to that surgery in particular, the most surprising aspect of that, or perhaps as the creator, the most rewarding part of it?
I was really surprised actually with such advanced surgery, how not invasive it appeared to be, because they were using a very thin, very small probe that's being implanted. So it doesn't require opened entire skull. It's just a small hole being drilled into the skull. And then this one-dimensional structure can actually enter into human, and the person even woke up in the middle of the surgery, or the patient was made to wake up during the middle of the surgery to perform certain tasks to check whether the implanted devices were in the right location. So it struck me that if we make our devices to have that kind of form factor, then it's potentially compatible with human. And so that inspired our NeuroString invention, that we basically turned the two-dimensional electronic skin into this one-dimensional fiber, so that we can get inside the human body minimally invasively.
That is fascinating. Okay, so moving outside of the operating room and the clinical setting, you've also applied your research to creating flexible screens for phones, computers. How have you been able to take something that is used, in an operating room setting and apply it to a real-world cell phone or tablet?
Yeah, so a lot of the materials we develop can also be used for consumer electronics. So there we work with the companies to transfer our technologies. And if the consumer electronics start to incorporate these materials, in turn, that can help to accelerate the medical electronics, because there needs to be a large kind of product base for a certain technology to really take off. So I think it's important to work on both sides.
Well, and as somebody who breaks a lot of devices, I wholeheartedly agree with you. How far are we from self-repairing phone screens, do you think then? Is that a possibility?
Some companies already incorporated coating onto the cell phone surface that supposedly can self-heal. It's not widely used yet, because still most of the phones use glass, and glass are pretty good in preventing scratching.
Gotcha. All right, so ultimately I know that you hope to use this technology to assist people who have maybe lost their sense of touch. How close are we to that, and how do you see that playing out in your research so far?
I think we're getting much closer now that we have the sensors. So we have also the ability to generate signal that our nerve can directly receive, and also our brain can directly respond to. So we have all the parts. Then now we have to figure out how to get the signal inside the body, and in a least invasive way, so that then the patient lost sense of touch can feel the sensation from the artificial limb.
Impressive. All right, final question for you. Your final thoughts. What are the hopes for the future of your lab?
Future of my lab, I think like many PIs now, with so much advancement in AI, I'm still thinking about how we can incorporate AI in our research to make our research more productive, and also advance the capabilities that we were not able to in the previously. But also at the same time, I see a lot of opportunities where our device are the devices that can actually collect a lot of data, generate a lot of data. So I also hope to utilize AI to take advantage of the data that we generate.
Wonderful. Well, thank you so much for your time today. We look forward to seeing what the future holds, and congratulations on your recognition this year.
Thank you very much.